I will begin with a word of prayer once I get up here. Heavenly Father, we thank you for this day again. I thank you for these students. Just ask you to bless our work today. Help us to glorify you what we do and just learn a little bit more about your creation, Lord. In your name I pray, Lord Jesus. Amen. All right, so like last time, we learned that if we have an inductor, right, then we had that the voltage dropped was what? Minus L di dt, right? That was sort of more or less what we learned. And it occurred to me that we never look at the question of equivalent inductance, and that's just kind of weird. Like, why don't physicists look at equivalent inductance? So I thought, let's try to work it out today, see what happens, you know? So example one, see if we can work it out. Suppose we'll start out easy. Suppose you have, you know, a voltage source here, right? You got a resistor, and then we've got not one, but two inductors, right? Let's say L1, L2, right? And as usual, I'll put a switch somewhere, right? And we're going to close the switch at what? Time 0, just to keep things easy. Just a little bit past time 0. So then my question is, what's the current as a function of time? And then perhaps once we do that, we can think about our life and understand what the equivalent inductance would be, right? What if the equivalent inductance would be, the idea would be we have the same circuit, but with just one inductor, right? So you guys want to guess what it's going to be? I think some of you already guessed last class, right? What was the guess? The equivalent inductance should be what? L1 plus L2, right? Yeah, that's what we're kind of expecting. And I don't guess it's going to take much work. Oh, famous last words, right? So, after we close the switch, we have that the voltage, minus IR minus L1 di dt, right, minus L2 di dt is equal to 0 by Kirchhoff's voltage law, right? If we label the current here I, right? Now, what's the initial condition? What's the initial current in this situation? Close this door, otherwise they get rowdy out here, especially with CFA. There's no telling what's going to happen. Remember, we've argued that the initial current must be 0 because there's no magnetic field built up in these inductors before we close the switch. After we close the switch, the magnetic field can't magically jump from 0 to non-zero over an infinitesimal time. I mean, over a small time, let's say. So we know that the initial current at time 0 is 0. All right, so we have that to look forward to. Okay, so what we got? We have L1 plus L2 di dt plus IR is equal to E, I believe. Right? If I move the negative terms to the other side, right? And then usually I like to divide by, let's see here, di dt plus, let's say R over L I equals to E over L, where L is going to be equal to L1 plus L2, just to make the algebra easier, right? At this point, you should have a strong sense of nostalgia because this is where we were, I believe, last class, right? Like, this is the differential equation we solved, is it not? As such, I will write the solution down, if I'm not wrong. I of t is equal to E over R times 1 minus e to the minus t over tau, where tau is equal to, oh man, I've forgotten. L over R, right? So in this case, L over R, which of course for us is going to be L1 plus L2 over R, right? So what happens after time goes to maybe we can graph the situation, right? It's easy to graph. Here's current, here's time. The initial current is 0. The final current is the voltage source divided by the resistance. And the graph looks something like this, right? And remember, by the time we're to 1, 2, 3, 4, 5, what on earth is making all this noise around here? Do you guys know? Because I hear this in my office sometimes. It's starting to drive me nuts. Like, I can't think. I'm just sitting in my office trying to prepare my next class, and all I keep hearing is, rah, rah, rah. Like, do we have a class in shouting or something? I mean, like, it's the what? It's the RTC room. Is it? Maybe it's the honors people. It's honors seminar, that's what it is. Whoever they are, they need to go outside.
Honors students outside?
Don't they have their own dorm? Can't the honors people go do whatever they need to do in their own dorm? In one floor? No. Okay, anyway, so after 5 time constants, you're 99.5% of the way to the steady state solution, right? At the limit, as time goes to infinity, what happens is that the inductors behave like a short circuit, right? The total current is just the voltage divided by the resistance. It's essentially Ohm's law for a single resistance, right? So in short, yeah, I mean, it's just what I was foretold, as foretold to me by you guys, is that the equivalent inductance is in fact L1 plus L2 in the case of series, right? So if you if you have a supply of inductors and you need to make a 47 millihenry inductor, and you happen to have 5 millihenries sitting around and 1 millihenry sitting around, you probably want to use 9 of your 5 millihenries plus 2 of your 1 millihenries in series, and that would give you a 47 millihenry inductor. I'm fond of the number 47 at the moment, for some reason. Example 2. Let's see here. No one knows why. Another example we could try, and I just, it just struck me, guys, like, why didn't I ever cover equivalent inductance before this point? Like, for what reason? I'll tell you why. It's because I wasn't taught equivalent inductance when I took a physics class from somebody, and I just accepted physics culture as you cover equivalent resistance, you cover equivalent capacitance, but you ignore equivalent inductance. Like, how incurious is that? I mean, it's like, I don't know, it's just a weird, it just struck me all of a sudden. You may be less amused by it than I am. So here, suppose we have this resistance, and then we have not 1, but 2 inductors this time. We'll put them in parallel, right? L1, L2, all right? And we'll stick with our voltage source E over here. So now what happens? Right? Now what happens? Well, now we need to think a little bit harder about the current, right? Because perhaps we could call this I'm going to call this I3. I'm going to call this one I1. I'm going to call that one I2. All right? How are I1, I2, and I3 related? I3 is equal to what? I1 plus I2, right? You guys. Oh man, that's not a good sign. I was trying to do 1 plus 2 and I did 2 plus 1. I mean, I guess it's okay, but it's just annoying. All right, so we have that. What else can you tell me here? How about this? Minus L1 di1 dt is equal to minus L2 di2 dt. Do you guys believe that? Where am I getting that equation from?
It's just the voltage across the inductor, isn't it?
Right, the inductors are in parallel, right? Well, L1 is parallel to L2, and parallel circuit elements have the same voltage across their terminals, right? That's definitely the case here. So we have that. What else can we say? We still need like a Kirchhoff's current law for the big loop, right? Current law is going to be voltage law. So I'm going to do like this, guys. Go, I'm going to go this way. That's the loop I'm going to make, okay? So if I make that loop, that gives me E minus IR. And which I? Be careful, which I? I3, right? I3R minus L1 di1 dt, and that is equal to 0. Now this is slightly scary because we have three equations, three unknowns, right? And some of them are kind of differential equations. So our goal here is to do what? We'd like to eliminate all but one of the currents and have a differential equation that just involves I1 or just involves I2 or just involves I3. How should I achieve that? I mean algebra, obviously, right? So let me clean up. Let me clean up this first one. The middle equation rather. I can rewrite that as goodness gracious, I don't know. I guess I'll write it this way. di2 dt is equal to L1 over L2 di1 dt, right? So we do have that. Let's keep that in mind. That allows me to, I think I chose poorly. I don't know. I mean, I kind of on the fence here. Any ideas how to solve these? Let's see here. If I can get rid of the I3 in here. I'm going to try taking, I think this might help. So we've got E is equal to I3R, right? Plus L1 di1 dt, yeah? All right. Now I3 is I1 plus I2, so let me put that in here, and maybe that I think that might help us. All right, so now we've got this differential equation just has currents 1 and 2 in it, right? I mean, I'm talking about this. Let me underline it. So what I have underlined in orange only involves the first and the second current, right? And this one only involves the first and the second current. Can I I may be discovering why we don't cover this right now. Yeah.
It's supposed to be L1 over L2 instead of L2 over L1.
Which way? Up there?
Yes.
No, I think that's okay. I'm just solving this equation here for di2. But I mean, of course, we could also, obviously, we could also trade this for, di1 dt is equal to, L2 over L1 di2 dt. We could do that, right? The other thing we could do that we haven't done yet is we could differentiate this equation and learn that di3 dt is equal to di1 dt plus di2 dt. That might be helpful. Maybe. But maybe not also. Well, I knew, let's see here. Another thing I might try is L1 di1 dt minus L2 di2 dt. The fact that this is equal to 0 means I can play games with that as well. I don't see it at the moment, guys. Anybody got an idea? Well, we'll just put a bookmark there. We'll come back to this in a future class. Hopefully, I'll figure it out. I mean, it definitely has a solution, obviously. It's a matter of me seeing past the algebra at the moment. I must stop. So. All right, so let's move on. The next example then. But I'm pretty sure, right, that what we should find eventually, right, if I would conjecture, right, I would conjecture that after a bit, after a little bit of struggling, we should eventually find that the equation E minus I3R, right, minus, no. Minus, sorry, my brain. L, let's call it L, di3 dt is equal to 0, where L is equal to what? We conjecture L should be equal to what? Yeah, L1 times L2 over L1 plus L2, right? This is our conjecture. I would conjecture that that's what should happen. You know? So that would look like what? So the question is, how do you get to this differential equation from the ones that I have on the board, all right? If we could achieve that, then we'd be home free, all right? Because then we go back to the same algebra and algebra and calculus we already did on the previous example today and the previous example last class. Or maybe I'm wrong. Maybe this isn't how parallel inductors work. Maybe that's why it's not in a textbook. Let's find out. I'm not going to find out right now though, because I've spent enough time and it didn't happen, so move on. So sometimes when something like this happens in class, students will inevitably ask me, so this is not going to be on the test? At which point I'll be like, no, that's not what this means. They're like, well, you couldn't do it in class, so I should be on the test. It's like, because you guys are smarter than me, so of course it could be on the test. I mean, come on. Let's see here. So, next example. But actually, this next example is actually not just an example, it's magnetic energy. So let's talk about magnetic energy. All right, so we'll start with the RL circuit. We have the voltage source minus IR minus L di dt is equal to 0, right? This is the Kirchhoff's voltage law, right? Which is an expression of the conservation of energy, guys. I don't know if you knew that or not, but that's what it's about. Kirchhoff's voltage law rests on the conservation of energy around the loop, right? Some of the voltage changes being 0. Now, so what this then says, if you rewrite this, we have, and I'm going to rewrite this and multiply by I, okay? So I've got E naught times I is equal to I squared R, right? Plus L I di dt, like that. So let's break it down. What are we looking at here? We should recognize these terms. So what is E naught times I? Power supplied by the battery, exactly. So this is the power supplied by battery, or the voltage source, whatever you want to. Right? The power is supplied by the voltage source. And where does it go? It goes into two things, right? On the one hand, it goes into power dissipated where? Dissipated by the resistor, right? So that's primarily what? Heat, something like that, right? The resistor gets hot as the current goes through it and bumps into the atoms and so forth. But then how about this other term? What's this? Power used in building up the B field in the inductor, right? So if that's the case, and power is what, energy per time? If we wanted to find the energy stored in the inductor, what would we do? So like the energy in the inductor should be what? It should be the integral of L I di dt, right? Integrated over time, right? And of course, you could think about the t's canceling, and we're just left with what? 1/2 L I squared, right? So there you go. The energy stored in an inductor is 1/2 L times the current squared, right? So like if if this circuit was set up so that initially, initially the switch was open, right? Then what would the situation be then? Well, initially there's 0 energy in the inductor, right? And then after a long time, what would the energy be in the inductor? What would this go to as t goes to infinity? How much energy would we store in the inductor at time goes to infinity in this situation, in this RL circuit? What's the current for infinite time, right? The current for long times is approximately just E naught over R, right? So eventually you would have stored the energy 1/2 L times E naught over R squared. That would be like the max energy stored in the inductor asymptotically for long times. So this derivation presumed that the inductor was in an RL circuit, right? But the truth that we just derived is more general than this. Like inductors and parallel combinations or more complicated circuitry would still be storing this much energy if a current I is going through them. So this is a general relation about the energy stored in an inductor due to the magnetic field. All right? Any questions? Nobody? All right. So, all right. Remember we worked out how much energy there was in the capacitor as well, and we figured out the energy density in the electric field. Do you guys remember that? Uh-oh. Well, now there's no hope. I'm erasing it. I mean, there's a chance one of you guys would have jumped in and saved the day and told me what to do, but oh well. I'll just save it for the test, I guess. Let's see here. So let me remind you, in a previous episode, right? We found that the energy in the E field, the electric field, right, per volume, it turned out it was equal to epsilon naught over 2 times the electric field squared. That's the energy per unit volume in the electric field. All right? So a natural question to ask is, how does this work out for the magnetic field? How much energy per volume in the magnetic field? So if we want to, I'll follow my example 82, which is on page 110 of my handwritten notes. And what we'll do is we'll think about a solenoid. All right, a very long solenoid. It's got current I flowing through it. All right. All right, current flowing through it like that. All right, so since the current's flowing, that means there's a magnetic field inside the solenoid, right? And which way would it be going? Which way would the magnetic field be going here? Right-hand rule, right? We think about it. So wait a minute. Oh, it goes, that's unfortunate. My picture's very unfortunate. It's supposed to go, let me make it like over here. So it's like coming up there and then around, right? So the current's coming down like this, like this, like this, like this, like this, okay? Like that. And so if you take your right hand, wrap around the coil, then my thumb will point in the direction the magnetic field goes. So the magnetic field goes to the right for the situation. Of course, the direction of the magnetic field is somewhat immaterial, but we also learned that B is mu naught Ni, where N is the number density, right? And what did we figure out? What else did we figure out the previous class? Do you guys remember? We found a bunch of different formulas, but what was the self-inductance of the solenoid? What was L? We worked it out. It was mu naught N squared AL, right? So this distance here is L, and the cross-sectional area is A, right? So it could be like A is pi r squared if we had to happen to know the radius and such. All right. So what's the volume? What's the volume of the solenoid? Yeah.
I want both sides of that equation. I don't think that's right.
Oh, this is unfortunate. Yeah. Oh, yeah. I'm sorry. This is my problem. I default to using an uppercase L for length, but I just cannot. That is a luxury I'm not afforded here, because capital L is pretty much set in stone for inductance. So yeah, my bad. Sorry about that. Yeah, hard to see the contrast of L with L, you know. All right, so great. What's the volume then? We're trying to figure out what's the energy per volume, right? So, okay, so how much? First of all, how much energy what's the energy stored? We do what, 1/2, there it is, 1/2 Li squared, right? So in this case, that's 1/2, well, let me just leave it like that. We got the formula for it right above. Let's just leave it like that for the moment. What's the volume? What is the volume of the solenoid? Where the magnetic field is that we're trying to quantify, you know, where the, assuming it's a very long solenoid, right? This is all approximate. You'll forgive me if I don't do all the calculus here. It does make me a little bit sad that I haven't done it. But I'll get over it. I'll get over it. So what's the volume? A times which L? The little L, right? Yeah, little L. Okay, so that's apparently the magnetic field energy per unit volume in the solenoid. And okay, so let's put in what that is. All right, so this is equal to 1/2. Now I'll put the mu naught n squared a little l. My current I will write as B divided by mu naught n. I got to square that because it's current squared, right? So this tells me that the current I can write in terms of the magnetic field, which is kind of a weird thing to do except for this derivation. But here it is, you know. The current in terms of the magnetic field is that. I don't usually think of it that way. I usually think of it as we have a current, it creates a magnetic field, right? But we can do the algebra here, solve for I, that we did, plug it in like that, divide by AL. So you see what happens is we've got some kind of nice cancellations going on here, right? The ALs, they be canceling. Oh, the n, we got an n squared, right? So what we got? We've got the n squareds cancel. I'm just going to circle that. That cancels with that, right? And one of the mu naughts cancels. We got a half. Looks like we've got a b squared divided by 2 mu naught. So let me make a summary here. Given an electric and magnetic field in some region, then what we would have to calculate is be epsilon naught over 2 e squared plus 1 over 2 mu naught b squared. This would be the energy, that's all, I'll call it du, u for energy, potential energy here, du dv. This would be the energy per unit volume in the electromagnetic field. There's some energy in the electric field, there's some energy in the magnetic field, and together, that's what you got. So if you wanted to actually calculate the total energy in some region, what would you have to do? So if we wanted to calculate the total energy in some particular volume, we'd have to actually calculate the triple integral over that volume of this quantity. Right? Which, as I have mentioned a few times in this class, Calculus 3 is actually really, really important because physics is three-dimensional and it involves rates of change, and as such, it is Calculus 3, right? Or differential equations, like all of it matters to understanding physics for sure. Any questions? So, again, I think it should be mentioned, what's really interesting about equations like this is that we're now sort of we're getting close to the point of studying electric and magnetic fields as being connected. right? I mean, we already sort of have that with Faraday's law. What was Faraday's law? Remember, how does it go? The voltage is equal to minus the number of loops in the coil, right, times d phi b dt. So this was Faraday's law. You can drop the n if you want, if you don't want to think about the loopy one. But let's just think about what that means for a second. Like, the voltage, we're talking about the voltage induced in some loop, right? What is that actually about? That's actually about an electric field in the loop, right? That electric field in the metal is pushing the electrons around the loop to make the induced current, right? To oppose the change in flux through the loop. But you see there's a link, right, between the magnetic field, which is changing, and the electric field which it induces. So we can't just think about electric fields. We can't just think about magnetic fields. We have to think about both of them and their interrelation to gain a complete picture of like how reality works. This is actually very exciting in terms of like what the ancients thought. There was not this link between electricity and magnetism understood very long time ago. This is a relatively recent thing that we've understood, maybe the 19th century, something like that. You know, at the start of the 19th century, you had understanding about, I mean, I think everybody understood lightning in static charge was somehow related, you know. But these other things like stones that attracted metal, magnets, why did that have anything to do with the other thing? Wasn't at all obvious. And then furthermore, the idea that light itself is electromagnetic wave, that was hidden until, you know, about the time of Maxwell, as far as I know. Of course, I'm not a historian, so anyway, we'll look more at that as the course goes on. But all right, so the next circuit to think about in here. So I'll have to come back to the problem we got hung up on today. We'll come back to it. But the next circuit, we won't get stuck on this one. The math is easier. Is the so-called LC circuit, sometimes called the LC tank. And this is a good one to talk about because it's exactly about, well, the story really is one of energy. So suppose you have a capacitor, right? And you got a switch. And over here you've got an inductor, right? Like that. So capacitor C, inductor L. And suppose, to start with, you've got a charge Q naught initially on the capacitor, right? So of course you got a minus Q naught down here. So suppose the capacitor is initially charged, then what happens when I close the switch at time 0? What's going to happen? The charge is going to flow off the capacitor, right? And it's going to do what? It's going to build up a magnetic field in the inductor, isn't it? Right? But then what happens after a bit is the capacitor wants to get charged back up again, right? So then it's going to take the, you know, anyway, it cycles back and forth is what happens. So the equation here, we got a couple of equations to think about. Oh man, I drew my picture backwards. My notes. I'll deal with it, it's okay. I've got to be careful not to mess up my picture. So I goes this way in my picture. So here we go. I is equal to minus dq dt. I mean, and the reason for that is we're talking about the charge on the capacitor, right? So as the current flows, the capacitor's charge decreases. And we also know what else? We also know that minus L di dt plus Q over C is equal to what? 0, right. You could also rewrite this as like Q over C is equal to L di dt. That would not be incorrect, you know. The voltage dropped on the inductor is equal to the voltage on the capacitor because they're in parallel here, right? Okay, great. So then this, when we plug this equation right here into this one right here, what do we got? Well, we've got ourselves a minus L d squared q dt squared plus q over c equal to 0. Oh, this feels wrong. Oh, I've neglected a very important thing, which is what? Whew, that was almost very bad. Yeah, the negative. What happens to that negative? Yeah, this becomes a plus, right? So it cancels. So when we plug the minus in here, that minus and this minus conspire to give me a plus, which is good news. Because otherwise we'd have like, it would be a totally different physical problem. I mean, the physics would be totally different than we're about to find. So here, this differential equation, you can rewrite as q prime prime plus 1 over LC times q equals to 0. The solution to a differential equation like this is a sinusoid. So in short, if we let omega equal to 1 over the square root of LC, then you can check if we set q of t equal to q naught cosine of omega t, we'll be in business here. My claim is that that is the solution to the initial value problem. So this is my claim. If you haven't had differential equations, the way we derive this will just seem like dark magic if I show it to you, because it's the result of like a week-long discussion. But trust me when I tell you, it's very easy to find this solution once you take differential equations. All right, like it's very, very simple. But for us, since we don't have that, let's just check that this works. What happens when you differentiate this function twice? What's q prime prime? Right idea?
It's negative w q sine wt.
Well, two derivatives though. So the first one gives you a minus omega q naught sine omega t, but then differentiate again, you get another omega, so you get a minus omega squared q naught cosine omega t, right? Which is nothing more than minus omega squared q of t, right? So what that shows you is that if we take q prime prime plus omega squared q, we'll get 0. But notice that omega squared, right? What is it? It's, you know, that's 1 over LC is what that is, right? Because omega was 1 over the square root of LC, so the omega here is for frequency. This is the natural frequency of the LC circuit, all right? So it solves the differential equations like I claimed, because you plug it in, it works. Does it have the right initial conditions? What happens when we put q of 0? Q of 0 is what? Q naught cosine of 0. What's cosine of 0? It's 1, right? So yay. All right. So what is the energy in this circuit at time t? We can work that out, right? So let's see here. So we have, draw the things together here. So on the one hand, we have found the charge in the capacitor. What does it do? Like I said, it oscillates, right? The charge starts out at charge q naught, and then it goes what? It goes all the way to charge minus q naught, right? And so of course we're just really talking about the charge on like the one plate. So you could draw like different phases. It starts out like this, all right? Well, I don't think I have enough time to draw everything at the moment, so let me not do that, but let me behave. I wanted to get to a point here. So if that's the charge, what's the current? I'm going to erase actually I'm going to erase the middle. All right, so what we have, what's the energy on the capacitor? Do you guys remember the formula? What was it? 1/2. What was it? Q squared over 2c? Is that right? I'm a little rusty. You guys got to help me out. It was Q squared over 2c, wasn't it? Am I right? Am I wrong? I remember it's also QV. 1/2 CV squared. Is this it? I'm actually asking. I'm right? Okay, good. Well, that's a relief. Okay, so what's the energy in the inductor then? Well, let's calculate the current. What's the current? Minus dq dt, right? So what's that? That gives us a what? Right? But the minus, they'd be canceling, right? Yeah. So we got ourselves omega q naught sine omega t. Okay, so what's the energy in the inductor? What did we learn? 1/2 Li squared, right? So in this context, 1/2 L times omega q naught sine omega t squared, right? Can you guys simplify that for me? What is L omega squared? It's L times 1 over LC, right? So L omega squared is actually just 1 over C. So you see this is actually Q naught squared over 2C sine squared omega t, right? So what's the energy? What's the total energy at time t? It would be the sum of the energy in the capacitor, right? Plus the energy in the inductor, right? And how does that work out? Looks like we've got a Q naught squared over 2C cosine squared omega t plus Q naught squared over 2C sine squared omega t. How's that? Can you guys simplify that for me? You're like, the answer is 47. What?
Q naught squared over C.
Q naught squared over, I'm going to insert a 2 in what you said. Q naught squared over 2C, which might have been what you said. But because sine squared plus cosine squared is 1. Does this make sense? Why should the total energy just be this? What is this energy? What was the energy on the capacitor to start with in this story? The capacitor was charged to charge Q naught. What's the initial energy in the capacitor? Q naught squared over 2C. See, this is the initial energy stored in the capacitor. And what this story is telling you is that that energy is shared between the capacitor and the inductor as it flip-flops back and forth and back and forth. But there's always still the same amount of energy here. Energy's never lost. Why? Because this is an idealization, for one thing. There's no resistance in this circuit, right? Do circuits like this exist in reality? Not really, right? We always have resistance, so there's always energy loss. But if there wasn't, this is what's called the LC tank circuit, because it's like a tank that, collects the energy and keeps it in there, like a water tank or something, but with electricity. Anyway, I'll shut up. Have a good weekend, you guys. Wait a minute, it's weekend? Yeah, it's the weekend. Yeah, begin your weekend.